Hello all, in this video we'll talk about how to use gradient descent with linear regression. So hope you have heard the term gradient descent whenever you have attended any machine learning programs or machine learning webinars. So here we go about knowing that. We know the machine learning algorithms fall under two basic categories, supervised, unsupervised, and we have classification, regression, and these are some of the tasks that are with the different machine learning algorithms, and you know different algorithms that are working in these categories, right? So today we'll move upon with how linear regression uses gradient descent to improve its performance, right? So let us have a recap of what is the model representation of a linear regression. Okay. So we know any training set must be trained with some learning algorithms to convert an X to predict or classify any output as Y. And we need a general hypothesis which works on that learning algorithm, right? For example, our X may be size of the house and our Y may be estimated price, and you need a regression algorithm that has an hypothesis. Why do we talk it as a hypothesis? The answer may not be accurate, however, it is approximate, taking account the uncertainty prevailing, right? So this is an example of how do we go for linear regression, right? So we try to draw a line here. Okay, so we know how does a linear regression work. So you can see here, this is an example of how linear regression works. So we have a single x, single y, and x of 1 is 2104, y of 1 is 460. So with this model representation, can I write like this, a linear regression? Okay. So H0 of x. So what is this H0? This is an estimation hypothesis function that is recommended for predicting this y. Okay. So it consists of one parameter x, and this is a bias, and this is the parameter added to this x. Okay. So let us have this as an h of x. So h of s is going to be our hypothesis function that approximates a univariate linear regression line. Okay, so let us move on with the cost function related to this linear regression. So our hypothesis is this one, and we need to find out theta 0 and theta 1. But how to do that? So when I have theta 0 and theta 1, so I have a mere assumption 1.5, I get a flat line because I don't account for x here. I make theta 1 is 0. So everything is 105, 1.5. And when I make bias as 0 and theta 1 is 0.5, I get a line like this. And when I have a bias is 1 and theta 1 is 0.5, it is 0.5. But what is actually the correct one? So we need to acknowledge the correct linear function, right? So we need a cost function related to that. We have to choose theta 1, theta 0 so that our hypothesis function is so close to y for our training example. We know about that, right? We talked about residuals and the distance between the line and the points. Okay, so this is our main idea for our cost function. So what is this? This is our predicted xi value and this is our actual yi value. The difference between these must be minimized. So you agree with that, right? So the distance between these two must be minimized. And so I'm making this as my objective function with my objective of minimization. And this m is the number of points in my data set. I added 2 on making my differentiation easier. Okay. We know this h of I is represented this one. And I make this cost function with represent this cost function with a term of j of theta 0 comma 0 1. So what should I minimize now? I should minimize this j function. This is called as cost function. So we can make a consolidation of everything. This is my hypothesis. This is my parameter. I have to make a smaller difference between my predicted value and actual value. So I make that as a cost function. So my goal is minimizing cost function or finding out the parameter theta 1 and theta 0 so that my cost function is minimized. Okay. So I can even simplify with one parameter. I can make it as 0 and I can only find theta 1 and I can minimize this one. So H0 as a function of x and j of theta 1 as a function of theta 1. So I am reducing only for showing what the gradient descent. So to depict the gradient descent, I am now keeping theta 0 equal to 0, right? So that I could explain this gradient descent well. So this is our hypothesis function and our goal of this one is here, right? So when I have a blue line, I have my j value as here, right? And when I have a green line, I have a maximized distance. So my j value is here. So you know what is a j value? It is a difference between the actual and the predicted. When I have my line as orange, I have a j value here. Okay. When comparing these three j values, which one should I opt for? Naturally and obviously, I will opt for this blue because this reduces the distance and it goes here, right? So I can have a line like this connecting my orange, green and blue, right? So my hypothesis is this one. So this is called as gradient descent where I'll try from this point and will move on slighter and slighter and come to a point where I'll have a minimized j value. Now coming to the both the parameters, I have explained with one parameter, but actually we have two parameters, so we'll apply the same here, right? So this is what we have talked earlier. From this we'll start. This is our cost function when it is drawn in 2D. Okay. So where should I be moving? If I start here, I should be slowly moving down where everything is minimized. So the point around this should be calculated as my parameter. Okay. So this is called as contour plot where I have see my original value is maybe here and slowly my j function gets minimized. Hope you understand with different, this is called as contour plot. First j value will be brown, then moving here, moving here, moving here, moving here, and finally it is getting minimized value. Okay. So this is where I should, again, I should find out the minimal value of this one. So I'm going to use gradient descent. I'm already having a function of j, which is called as cost function, and now I'm finding out the minimum value where this parameters minimize this value. So I'll randomly start with some theta 0 and theta 1, and very slowly I'll keep on reducing this value until we hopefully end up at minimum. This is a simple algorithm of gradient descent. See, I'm starting from here and moving and simply, see, okay, I'm starting from here and I'm trying to make my path so that I get a minimal j value. Okay. So this is the algorithm of your gradient descent. I have to repeat some procedure until convergence or you find a very less difference between the previous theta and the present theta. The present theta will be calculated as the previous theta minus the differentiating function with some learning parameter, right? So this alpha is called as learning rate or the step size. And this is called as derivative. This is the ultimate function of a gradient descent when you subtract something from the original value to get the minimal value. So we have a simultaneous update. I have theta 0 pointed to temp 0 and I have an adjustment in theta 1 and then I'm calculating temp 1 and only then I'm reassigning everything here. See, be very clear. I'm not changing temp 0 and immediately assigning to theta 0. As in the formula, we have theta j will be immediately assigned, but we have to find out both of them and then assign those values to them. So you need a simultaneous update of both the parameters, right? So whatever the size of the parameters, whatever the count of the parameters, they have to be simultaneously updated and then reverted back to the original. I have told you the same. This is incorrect. This is only correct. So this is how gradient descent starts from an theta 1 and finally slowly goes down and find out a minimum value. Right? So it starts. So when you have a greater learning rate, alpha, so when you have an alpha value of greater value, then you may have a learning rate like this. First, your theta 1 might be this one. And next your theta 1 might be this one. Then your theta 1 might be this one, this one. So if you have a big learning rate, you may not get into a correct minimum. So have a very small learning rate like 0.001 or 0.01 and slowly, steadily, please progress. Okay. So this is the gradient descent algorithm for the linear regression. We have to repeat until convergence and we have to update it. So when I have a partial derivative of this one, so the formula has a partial derivative, right? So we are working on that part. I'm deriving. When I derive this formula, this 2 comes here and it gets cancelled, and your value for theta 0 will be like this, and your value for theta 1 will be the same thing, but theta 1 coefficient is x, so we have an x here. So this is the derivative for both. So now I am adding this derivatives to the formula. See, so this is the original value, this is the learning rate, and this is the derivative of our cost function for theta 0, and this is the derivative of our cost function for theta 1. Not a very big difference, but only an xi is added here. Update theta 0 and theta 1 simultaneously and then assign the value. Repeat until convergence. So this diagram may help you to understand how it moves. You start with a random x down and slowly and steadily it moves to the necessary linear regression point. So I think we have 28 iterations for this data. This is how gradient descent works with an initial value of parameters and then improves itself. So we have a specific batch gradient descent until we have to use for all the training exams, right? So now you can look for another part called stochastic gradient descent. This is your reference. What is stochastic gradient descent, right? So this is all about your gradient descent discussion. Thank you all. Bye.